Hello, everyone, and especially to the ones who are joining us from North America, because I understand it's very early in the morning, and also from our friends in Asia, where we're late at night. So I'm Valérie Faudon. I'm the Executive Director for the French Nuclear Society, and this is the second session of our Index Conference, which is international conference on digital transformation in nuclear. There's about more than 500 of you who have registered for the conference from 30 different countries, so we have a very international audience. So there will be 9 sessions total that has been prepared for you by our program committee. So I hope you can attend the 9 sessions. If you're missing one session, there will be replays on our YouTube channel. And of course, we encourage you to talk about the conference to your friends and colleagues, so we have more people who can benefit from the session. So I will now give the floor to Jean-Eudes Guilhot-Gaudeffroy, who is the Director of Digital Excellence Center for Assystem. So I leave you the floor, Jean-Eudes, for this great session on digital twin.
Thank you, Valérie. Good afternoon or good morning, as we understood it's 5 a.m. on the west coast of America. So the subject of today, the subject of this keynote is quite exciting topic. In fact, we are going to talk about the current status of digital twin deployment. Let me first introduce the 2 speakers that I have today with me. First of all, Nick Touran. Nick is a PhD in nuclear engineering. He has spent, in fact, he's still working. He has spent 13 years at TerraPower, working in several positions from design, business development as well, engineering, and is now a digital engineering manager at TerraPower. So good morning, in fact, Nick. And the second speaker for today is Patrick MORILHAT from EDF. Patrick has been working and is still working 30 years for EDF, as well in different positions in project management and research program management. Today, Patrick is managing the nuclear plant performance R&D program, so at EDF. Good morning and good afternoon to you both. So as to introduce the subject, so as you know all, digital twin are a digital representation of a physical asset. An asset can be an installation, a process, or even an equipment. The purpose is to be synchronized with the physical world, and that is something which is quite important in the digital twin, and the digital twin can help to face various challenges, can help with in fact numerous use cases. So where do we stand today on their deployment? We today are going to have the perspective of a startup company, let's say TerraPower, and a major nuclear operator, so EDF in this case. Starting with you, Nick, from your perspective, in your context, what would you say about digital twin implementation, use cases, challenges?
Sure. So thanks. Very happy to be here. Hello, everyone. Coming from Seattle, Washington in the US. I'm going to share a couple slides to talk through that question just for a few minutes here. So let's see. Should be seeing some slides. So it's interesting so when I started at TerraPower, and just by the way, TerraPower started back sort of in the mid-2000s, focusing originally on a traveling wave reactor, which is basically a breeder reactor that doesn't do reprocessing. Instead, it uses very high burnup once through cycles to get most of the benefits of a breeder reactor without the complications of reprocessing. That requires very high burnup fuel. And so at this point, we're actually making a more traditional sodium-cooled fast reactor that will that makes sense in today's markets, and will eventually, as we develop the higher burnup fuel, will sort of asymptote out towards that initial goal. Since we didn't start with a physical asset, we can't have a digital twin at first because we don't have something to synchronize it with. And so I was thinking about this question through the concept of the life cycle of a digital twin, because a lot of the information and data that goes into a true digital twin in the construction and operation phase starts in the early phase. And so we've really focused on originally the conceptual design, but in the last 15 years or so on more detailed design of a sodium-cooled fast reactor. And we also have a molten salt reactor design, by the way, but most of our focus has been on sodium coolant. And I think the interesting thing is that, you know, if you have a digital twin which is synchronized with physical reality and has a bunch of models that can interpolate the details of the physical model or of the actual physical reality, and also extrapolate in time, you really need really detailed models, and those models can be the same exact models that you do in the engineering phase. And so we've focused most of our time building a lot of engineering models, and we've also put a ton of time into automating the connection and coupling of these engineering models. And we believe that's really going to, as we go into construction and operation, that's where the connection to the digital twin and all the benefits that we seek out of a digital twin are going to come from. So that's what I'm going to talk mostly about today, is how we've kind of prepared for that in this early life cycle and sort of the pre-digital twin. So we built an integrated simulation system, and basically what you start with is a software model of a reactor, which is this thing in the center here. It just has the dimensions, the materials, material properties, and so on. And then we wrote code that can read off of that central model and prepare input files for more specialized neutronics models. We use things like DIP3D and MC squared. You may use Uranus or Apollo, things like that. It can then importantly execute these particular codes and then read the output files and load the results of the output files back onto the central model. And so now the central model, which represents the reactor, now has power distribution, reaction rates, and so on. And that's enough information to do the same on the thermohydraulic side in the core. So you can now build thermohydraulics inputs, run a particular thermohydraulics simulation, bring the state variables back onto the central hub. And so you can continue. And so you're basically adding more and more state onto the system. And as you go through, so then now you have flow rates, temperatures, pressures, then you can do fuel performance, and then you can run plant transients, you can do kinetics, you can do core mechanical. And so all those things can be sort of automated through this hub and spoke model. And this, again, we did this originally because we needed to be very efficient. We're a tiny company at first. We had to do lots of analysis. And so we did it sort of for the analysis efficiency, but it turns out that this is also basically essential to capture the values of a digital twin as you move forward. So the implications, I think, are pretty straightforward. Traditionally, you have different specialists running different types of codes and passing information around, but when you automate it all, you can have any analyst run the whole thing. And essentially for this topic, you can have a computer sitting there running the entire integrated analysis system with sort of a click of a button. And that's important for going out and trying out different things or interpolating. And I won't dwell on it too much longer, but just the sophistication that we added to automate, we really are kind of proud of. So you can sort of click a button or evaluate this big function, and it'll go through and it'll compute all your cross sections. It'll do all the it'll do fuel management optimization. It sort of looks ahead and tries different options for each cycle. It can do equilibrium cycle analysis, pin power reconstruction, all your basic, I mean, all your important analysis at the core side. So, so this is, again, a very powerful physics evaluation function effectively, all the way out to levelized cost of electricity as well. So anyway, and then as we go into the more detailed design of the plant, we start looking at things like configuration management of the plant itself. And if we go out and read some of these documents like the IAEA Tech Doc 1651, and then there's an EPRI document about data-centric configuration management, it becomes clear that the data needed for standard configuration management is the same data needed for this integrated analysis tool and also for the digital twin going forward. So this is all combined, and I think everybody's seen this configuration management equilibrium 3-ball, where you have, why you're designing something the way you are, what you say the design is in the design documentation, and then what the actual physical configuration is. And keeping these things synced up is the topic of configuration management, and that just so happens to be the exact same thing that a digital twin allows you to do and rides on top of and sort of enhances. So a digital twin can kind of ride on top of a configuration management system and provide additional insights, additional interpolations, and many things. And so that's sort of what we're moving towards. And so in order to connect the dots between configuration management and an integrated simulation system, you need a configuration management information system as well. And so we actually have decided to go ahead and start building our own relatively lightweight configuration management database. It's basically a relational database. It has lots of different relationships between the types of information in the plant, and then it plugs into commercial tools like the Aviva suite, for instance, and it plugs into our analysis tools, and it runs a lot of our process and design change control procedures. And so this thing is sort of, it steps you through what is happening with the design, how it's changing, why it's being allowed to change, and then as the design changes, we sort of we're trying to automate, keep the models up to date, and then once we have the actual plant, we'll be bringing in inspection data and sensor data, and that'll sort of be the fully integrated digital twin is the hope. At which point we'll start getting these benefits, which we'll hear about from Patrick, which are sort of related to predictive maintenance, optimization of the fleet, and so on. Okay, almost done here. So just the types of data that we're starting to look at. So we've created this system and we've started loading up different data tables and connections. And this is just a really high, broad overview of all the different things. We need to have information about the organization, the project hierarchy, so that we can run the procedures, so you can know who's allowed to approve certain changes and so on. All of our analysis software and its current verification status has to be known, because as you're doing a certain analysis, you need to flag whether or not that's a qualified analysis. We have various risks, different plant decisions related to plant requirements. Plant functions are related to PRA, different event sequences, and these all sort of flow down and tell you what your safety classification has to be. It turns out that keeping all this in your head or on a spreadsheet is so challenging that there's a huge benefit in putting it in something like a relational database and getting it all connected. And so we've really found that having this in, again, a pretty lightweight but very customized nuclear specific database is quite valuable. And then of course all the configuration is within the plant breakdown structure, where you have your different lists of equipment and all the parameters and so on. So anyway, that just is sort of like where we are in the transition from integrated design models towards a digital twin. As we start loading up sensor data, we believe there's a lot of value you can get by taking those models. You can directly use them if you automate them, and that automation is important. The configuration management during preliminary and final design is directly usable in a digital twin if you integrate it with the other systems. And we also believe that things like the equipment reliability data that's going into your PRA is essential to really capture the value down the road. As you're trying to do maintenance planning, you can go back and look at those databases. So anyway, that's kind of where we're at. So I'll stop there. Thanks.
Thanks very much, Nick. In fact, what is quite interesting, I think, is that you start greenfield. So obviously, you start without connection to the physical model. But I understand you prepare your modelization to allow for those connection in the future. That's quite interesting. I take this opportunity to say that anyone can ask question, because I don't see any question on the team so far. But feel free to ask any question to the speakers. And so we will continue with you, Patrick. From EDF perspective and mainly on the fleet, on the operation of the fleet, will be interesting to have your view and insight on that front.
Yes. Can you see my slides?
Yes.
Okay, so thank you, Jean-Eudes, and thank you, Alex. Yes, so my topic would be to focus the conversation about digital twins for operation and maintenance of the existing fleet. As you know, EDF in France, which is a French electric utility, has about 56 plants. And based upon this strong legacy, we have been developing digital twins for different purposes for now about more than 10 years, so to speak. In fact, a digital twin is not a new concept. It is a new version of an old concept. And this old concept is very simple. When you operate a plant, it's quite difficult to see exactly what happened in the plant because you have toggles, you have buttons, you have displays and so on. You have voltmeters. But what is the physics there? Quite difficult to see it. And these digital twins, and before the tools were called monitoring or e-monitoring, all this kind of stuff, were exactly devoted to that, to see exactly what happened in different parts of the plant. So we developed digital twins mainly for three purposes: for training of people, operators in the control room, also field workers. So training is very important for people to rehearse their operation before an outage. For example, when the building is closed, it's easier to prepare well in advance what they have to do with a digital twin. We have also digital twin for operations, that is to simulate specific transient. For example, when we the French fleet is very flexible. So when we go from 100% to 20% of power, you can simulate what is the impact on the fuel rods in the core, for example, using a modelization, a very accurate modelization plus data coming from the field. And the last point is very common. It's about maintenance. So it's about for developing diagnosis for maintenance, predictive maintenance, preventive maintenance, and so on. So it's a well-known field for development of digital twins. So in my slide, I will give you only 4 examples of the types of digital twin we have developed in the recent year, and we are still developing. We are different level, in fact. We have the level of the components, the level of the reactor itself, the level of the building, that is a concrete, and the level of the field operations, because when you look to an outage of the plant, it's a kind of a living organism with a lot of people involved in different parts of the plant, with a complex layout, with different states of the reactors, and you have to get a complete image which is living of this status. So starting for the level of the component, we have developed a steam generator digital twin and a turbine generator digital twin. For the steam generator, the objective is to understand the clogging effect. When you have a steam generator, you have a lot of tube bundle, and you may have some clogging because of water which cool down these tubes. We have some impurities, some deposits in it. So problem is, do we need to launch a chemical cleaning of the steam generator or not? Knowing that the chemical cleaning of steam generator is a very long activity, it's very costly, about 15 million euros each. So therefore we have developed a digital twin for that, mixing chemical modeling of the steam generators, using data from the field, using also non-destructive technique examination images, using report of maintenance. So for that you need to have artificial intelligence, you need to have a 3D modeling, you need to have a natural language process models to exploit what is in the maintenance report and all that stuff. So we have put that in place. We are currently developing and deploying this tool on the fleet level. And by the way, we are saving many times 15 million euros by using this steam generator. We did the same for turbine generator. I don't want to insist on that one. Going to the reactor level, very important. Reactor level, it's again, you look completely to the primary circuit of the plant plus the vessel. And the question is, you mixed what happens in terms of neutronics in the core, in terms of thermal hydraulics, in terms of thermomechanics, to give the operator the view of what are the phenomenon at play in the reactor when again you have to follow some transient, you have to shift from one state of the plant to one another, and so on and so on. So this project is a common project we develop across the French with other partners of the French industry, and which is going on. And the objective is to use it not only for the purpose of operating the plant, but also for preparing studies of new plant or modification of the plant and so on, more for engineering stuff. We have also a digital twin of the building, the concrete building itself, because the concrete is aging, and the problem there is to evaluate the tightness of the building. It is done for the two-wall plant type. So we have a mock-up, one third of a standard 1300 megawatt power plants, full of sensors. We have a complete 3D modelation of this mock-up, and because it is one third of the final size of the plant, it accelerates by a factor of 9, in fact, because it's a cubic, the time. So every year, by following this digital twin, we can extrapolate what will happen in 10 years from now for a specific plant. And by the way, we are preparing the 10-yearly outages that are required by the French regulation, and to understand where is do we have some evolution in the tightness, where to put some polymers to make the tightness less than it could be, and so on. So it saves something like 30 to 40 million euros per year. Very valuable. And the last one is about field operations. So we have completely built a mock-up of different plants in France by using a laser scan, 3D video, using drawings, using computer-aided design maps, and so on. And then with this digital model, we have the layout of the plant. We have the status of the plant, the technical specification. We have the resources, how many people work in a certain period of time during an outage and where. And we have the planning, the list of activities. And as the outages evolves, we are in real time making an update of this digital twin to see if we will have some problem in maintaining the duration of the outages, or in managing conflict between two activities that occur in the same time in the same room, or one activities which requires different rooms to be managed, all this kind of stuff. And it works quite well. So we have developed that for the 900 megawatt fleet, then the 1300 megawatt fleet. We are doing that now for the new EPR. And it's, again, very, very useful. So coming to the next slide, you can consider the digital twin like an iceberg, with the digital twin, which is the emerged part of the iceberg, but a lot of underlying challenges behind that to complete and to achieve digital twins. The first one is about modelization. So we need high fidelity physics-based model. So as you know, we have historically, as every company, we have developed a lot of 3D models for one physics, for example, for neutronics, for mechanical engineering, for thermodynamics. And now for this digital twin, you have to link all this physics in the same model. And you have different scale, and you have a multi-scale approach. So it requires a lot of activities to be sure that your model still fits to a good level of quality, and then to make them run quasi in real time, because in a digital twin, you need the real time, and sometimes faster. You need to run your model faster than real time. So this is a huge challenge that we are addressing right now. As opposed to that, which is a more model-driven approach, we have a data-driven approach using artificial intelligence and machine learning. And then there are a lot of solutions for machine learning, but you know that the main problem there is data, because there is no big data without data. And the quality of the data is very, very key. And data harvesting is key, because as opposed to what Nick presented, when you are addressing existing fleet, you have a strong legacy of documentation of data that are not digitally based, because they date from the 80s, the 90s, and so on. So we develop a huge activity and develop some models to automatically digitalize all these data, to get them, to put them in some big data lakes, to learn the computer to understand this data, and then to read the data before processing and going for machine learning and AI. And we consider that 70% of the time on this topic is not devoted to machine learning or development, but to getting the data and cleaning the data. And this is very important to know, because data has very high cost. And this makes a big part of the cost of digital twins. Once you have 3D models, machine learning, and so on, so you have to couple all this model-driven approach and data-driven. So you have to mix different techniques, finite elements, reduction of model, machine learning, natural languages, and so on. It's a problem in itself. You have the problem of scalability and performance, because you can do that for one plant, but if you have a 56 plant, you have to multiply everything by a factor of 56. So you have a question of scalability is a tough question, you know. So you need behind that the big data lake. You need to manage your data. You need high performance computing capability, all this kind of stuff. When it comes to configuration management, as Nick said, it's very tough problem, because you need to ensure that your digital model, your digital twins that you are building now will evolve accordingly to the plant, because the plant will evolve. We'll have some modification. We'll have everything can happen on the plant or the component that you are following, and your model has to evolve accordingly. We have also another problem that we call extended enterprise. By there, we mean that as EDF, as the operator, we are not alone. For example, during an outage, 75% of the value is not done by EDF people, but by subcontractors, partners, and so on, manufacturers, all people working on the different part of the plant. So, and all these companies have their own digital twins. So how do you manage a bunch of different digital twins which are supposed to address the same components or the same problem? It's not easy. So question of interoperability of the platform occur, of the software, question of standard and protocol, data governance and ownership, who owns the data at the end of the day, and intellectual property, all this kind of stuff it's not completely technical problems, but it is really a problem. We have also regulatory aspects, because when it comes to safety case or things like that, or components important for safety, you know that the safety authority are very reluctant to that we could use black boxes and probabilistic models or things like that. So the question of the confidence that you can put on all this technology, and specifically artificial intelligence, is very key, not to mention cyber issue that can occur. And top of that, where is the value there? And it is not always very, very easy to see the value. You can see clearly the costs, but where is the value is not that easy. So we have to set up business cases, and business cases include also the social aspects and the organizational aspects. That because when you put a digital twin, normally you make sometimes you change the organization of the work, you change the organization of your company, the responsibility between different sectors of the company. So all that has to be considered for when we go for a digital twin. So my final point on that, I guess you need, I would like to give you two messages to keep from our presentation. First, you cannot develop digital twins for everything. You have to focus where is the most valuable problems, because, second message, developing digital twin is very, very costly. You know, some say that data has value. In fact, it is not true. Data has a cost, and the information you get from the data has a value. And the journey between data to information is very, very, very costly. So you have to consider that, and to develop again digital twins only for the business case, which are very, very relevant. So this is my final point for my presentation. Thank you.
Thank you, Patrick. Very interesting insights. From your perspective, I think what we can see is that there is no just one digital twin, but in fact as many digital twin as use cases, because we are talking about digital twin for a turbine, for instance. It's not the same as the digital twin for a complete reactor, for instance, or even for a process like the activities on the maintenance side that you to describe perfectly. The other point, I think, is that between Nick and you, I think the difference, as you said, is that there is a huge legacy to take into account when talking about the existing fleet of EDF. For sure, that's a challenge. Some question, in fact, I'm not very sure we will have the time to address them all, but so there is one interesting question, which basically, it's for you, Nick, but I think both of you can react on that. It's a quite key question, which has to do with the licensing process and the question of the safety authorities that you touched a little bit, Patrick. So there is a different question on that front, but the question would be: do you think that we can use digital twin one day to have the safety authority validating the product, and to which extent, let's say, typically in the US, would be interesting to know, are the safety authority prepared to work through a digital twin? Nick.
Good question. Thanks.
Tricky one, by the way.
Yeah, it's a bit tricky. Let's see. So on one hand, configuration management is required by regulation, and so that element of digital twin is sort of everyone's used to. It's like, show me the configuration and how you validated it, and so that's a big part of having a digital twin. And so I think they're fully prepared to handle that particular aspect. And then these integrated models that do the simulations around them, a lot of those we are using for licensing independently of the digital twin. I mean, as I sort of mentioned, it's like the preliminary element of the digital twin. And so, I mean, having that come together and provide a licensing basis is something we're working on, and we've done plenty of white papers and interacted with the regulator. They're fully on board with the plan. I mean, the US NRC, the Division for Advanced Reactors, is actually using a very integrated data model for a lot of their confirmatory analyses. So they call it Blue Crab. It brings in, it has a moose-based framework and brings in a bunch of different simulations, not unlike the thing that I showed that we're working on. So they're pretty familiar with that type of approach. Now, there are some questions about, like, well, if you're doing automatic coupling, like, do you have to do validation of the data exchanges in addition to the individual physics modules? And I mean, if you want to use it directly, you do have to do that, but there is the backup plan of saying, well, even though we can run it automatically, for the case that we're submitting for licensing review, we will do manual reviews of the different input files for each thing in isolation. So, and that's much more traditional. So that's so what we're planning on doing is going with the individual exchanges at first, and then if we do get to the point where we find it valuable to actually validate the automatic data exchanges, then we'll perform the V&V of those as well, and then use that. Hopefully that answers it to a degree.
Patrick, on that front, I mean, on the safety authority point of view, maybe with the French, I would say éclairage, if I may say.
Okay. In fact, we don't use digital twins for safety case or safety related activities, because it would be very difficult to demonstrate validity. When it comes to safety authority, we have only some requirements to follow. There is a guide issued by the French Safety Authority for scientific computer tools, the guide number 28. And when you develop scientific computer tools for safety case, you have to follow this guide. But when you don't address any safety case question, for example, all the example I've given were for training. So training is not a question for safety. There is a question for safety, but as long as you stick to the certain competencies, it's okay. For maintenance is a question for operators, not for the safety, as long as the components follow the duties they are supposed to follow. And for operation, it's the same. As long as you stick within the technical specification of the plant, the safety authority has no question. So because the digital twins we are developing are more aids for training, aids for operation, aids for maintenance, and are not directly linked to the process itself. Okay, we don't pilot and operate using these digital twins. So as far as we stick to that, there are questions of interest, but there are no safety questions raised by the safety authority. If the times come to go deeper and have a retraction of the process or things like that, there we will have some question. And mostly we still have we know that there are a lot of questions regarding machine learning, artificial intelligence, because these are black boxes, and it's very, very difficult to understand exactly what is the behavior of this algorithm, and to demonstrate the deterministic aspect of this algorithm.
Another question. So, in fact, many questions linked to the question, which is how can we make sure that the digital twin, which is a good one, this one, is up to date with the physical world, and in fact, do we need to, or are you working on the improvement, any improvement on the data acquisition field, the measurement fields? We are talking about IoTs, for instance. So Nick, what do you think?
So the way I see it, you should use, and what we're trying to do is use the same database, the single source of truth. We want that configuration management database to be the one and only database that represents the configuration of the plant. We want that to be used for standard configuration management practices, and also provide inputs directly to any of the models that are being used for digital twin purposes. So literally using the same data set, which is this huge, it's a massive database representing all the equipment and a lot of people and a lot of tasks and project information in a big relational database that's used both for configuration management and digital twin. So that if you do that, then whenever you change something based on some new measurement or new data acquisition that you get, then it's already in the database, and next time you go out and run the digital twin, it's already up to date. And I think if you don't do that and you try to have multiple databases that you're syncing up, you'll run into so many challenges related to synchronization, conflict. It seems almost overwhelming to try to keep those synced up if you don't just use the same database.
Right. And Patrick, on the install base, do you already have all the sensors you want and all the I would say the data acquisition needed, or are you working on that front as well?
No, we have not, because putting a sensor on nuclear plant is very costly. So we are using what was designed at the beginning of the plant, plus some extra sensors that we put. We have developed the use of 5G, of new IoT infrastructure. But we have focused some development specifically when it comes to configuration management, specifically to handle the discrepancies between the design of a pipe, for example, and the pipe as built, because there are always some differences, you know, what was expected on the drawings and the reality, because the changes, the plant has a long history, many changes have been done. Sometimes the changes have not been reported for some reason. So and on top of that, in France, you know, we have different series, and a series is, for example, 900 megawatt reactors. On the paper, all these reactors should be the same. In fact, they are not exactly the same. So when you develop a digital twin for one plant, you take one plant of the series, but after that, you have to adjust the discrepancies between that plant and the other one. And for that, we have developed a specific tool. For example, when it comes to laser scan, 3D photograph drawings, we have developed automatic tools to adjust these discrepancies between different plants. Even if they are supposed to be exactly the same, they are not. And then to adjust the digital twin we have developed. So we have one digital twin per plant, in fact, for some of the use case I have shown.
Almost. We are touching the end of the conference. In fact, maybe one last a little bit philosophical question, which is what are the limitations of digital twin? In fact, are they still today? Yes, of course, any activities that cannot be simulated, or what are the tricky ones? What would you say, Nick?
Yeah, I mean, I think the most obvious limitation, I think, just reflects the thing that Patrick said at the end, which is that the value, there's a lot of hope for the value of digital twins in terms of cost reductions, but actually achieving that value and making sure it's worth the cost is a little bit nebulous. And so it's not a sure shot. You know, if you use a digital twin, all of a sudden all of your economic problems go away. I think that's clear to everyone in this conference that that's not just an automatic thing. And so really finding the places where using computation and modern computers and databases and simulations can actually help is a big challenge. And I think that's probably going to be in various change impact analysis, work planning. A lot of the human element and project management element is probably where the biggest actual cost reductions will come in. Are there things that can't be simulated? Sure. I mean, there's a lot of processes. I mean, things like fuel performance in an advanced reactor. You know, we don't have a whole lot of data on the equipment reliability or on the fuel performance or anything like that, because the data just does not exist. And so you can't do a lot of machine learning or predictive things for things that you don't have any actual physical experience with. And so there's limitations there that have to be recognized. So on the other hand, we do know, since it's sort of a first of a kind, we need to be collecting data. The data we collect from this plant, the first plant, will be very valuable going forward. So we want to make sure we capture it in a way that it will be useful down the road. So that's a pretty big limitation.
So we are not completely finished with physical models, and Patrick, you confirm, I guess.
Yeah.
So we are at the end of this keynote. First of all, thank you again, Nick, for having woke up so early in the morning to be with us, and Patrick as well. Thank you for your participation. So just to conclude, in fact, that we are not completely finished with this journey of digital twin. And also, please do not forget, I mean, to all the participants, that Index will continue. In fact, Index will resume on December 15 with a conference or webinar on design and simulation. So thank you, everyone, and see you soon on Index again. Thank you.
Thank you. Bye-bye.
Thank you.
Bye now.
Thanks for having me.